Welcome to ThirdEye Labs, where we make the unseen seen. Today, Markov chains. Our story starts in 1906, in Russia, with a mathematical brawl. Pavel Nekrasov, a mathematician and a deeply religious man, made a bold claim. The law of large numbers, he argued, only works when events are independent. Since real data still averages out, human choices must be independent too, and that, he said, was a mathematical proof of free will. Andrei Markov, nicknamed Andrei the Furious for his temper, found this absurd. He set out to prove that even events chained tightly together, where each one depends on the last, can still obey clean statistical laws. No independence required, and no free will smuggled in. What started as a mathematical grudge became one of the most useful tools ever invented. Within decades, his chains were describing diffusing particles, powering Claude Shannon's theory of language, and eventually ranking the entire internet. To settle it, Markov reached for poetry. He took the first 20,000 letters of Pushkin's novel in verse, Eugene Onegin, and sorted every single one into just two buckets: vowel or consonant. Then he asked, does the next letter depend on this one? Watch the idea on a few letters. On a tiny sample, the counts are rough, but Markov did it for 20,000 letters, and the pattern was unmistakable. After a vowel, the next letter is a consonant about 87% of the time. After a consonant, a vowel follows about 66% of the time. Letters are not independent at all. They form a chain, and yet the long-run frequencies are perfectly stable. Nekrasov was wrong, and Markov chains were born. Here is the heart of it. Picture a frog on lily pads. Where it jumps next depends only on the pad it sits on right now, not the winding route it took to get there. The past is forgotten. That memoryless rule is the entire definition of a Markov chain. So why does looking only at the present matter so much? Sometimes it is all you need. To finish "the cat sat on the blank," the last few words already point you at a floor, a mat, a roof. But now try this longer one. The cat sat on the roof and looked at the blank. Suddenly the best guess leans on words from far back: the cat, the roof. Markov's bold move was to throw all of that away and look only at the current state. It is a daring simplification, powerful enough to rank the entire web, yet simple enough to compute in an instant. Hold on to that tension. It returns at the very end. Let us make the machinery concrete with the weather. Each day sits in one of three states: sunny, cloudy, or rainy. So here is a quick game. Today is sunny. What is tomorrow? Take a guess. The chain says sunny 70% of the time, cloudy 20%, and rainy 10%. Every state carries its own set of odds. Watch the weather wander, where each hop looks only at today, never at the whole week before. All of those odds collapse into a single grid, the transition matrix, written P. Each row is a starting state, each column is where you might land, and every row adds up to one, because tomorrow has to be something. Brighter cells are likelier jumps. The entire future of the chain lives in this little table. To step the chain forward, you multiply your current spread of probabilities by P. Today we are certainly sunny, so the row is 1, 0, 0. Multiply it by the first column and you get the chance of sun tomorrow. 1 times 0.7 plus 0 plus 0 equals 0.7. Do that for every column and out comes tomorrow's forecast. The whole rule is just pi times P. What about 2 days ahead, not just one? You simply multiply P by itself. P squared gives the two-step odds, and P to the n gives n steps. Here is the punchline. As you raise P to higher and higher powers, every row marches toward the very same numbers. No matter today's weather, the far future forecast is identical, and those identical rows are the stationary distribution again. Now start sunny and just keep multiplying. Step by step, the spread shifts and then something beautiful happens. The bars stop moving. They settle onto one fixed spread, no matter where we began. We call it the stationary distribution, pi. It is the chain's long-run personality, and it satisfies pi times P equals pi. If that rings a bell, it should. Pi is a left eigenvector of P with eigenvalue 1, the exact idea from the eigenvector episode. And you do not have to sit and wait. You can solve for the stationary distribution directly. Saying pi times p equals pi just means a step leaves pi unchanged. Move everything to one side, add the rule that the probabilities must sum to 1, and you have a small system of linear equations. Solve it once, and the exact long-run fractions drop out. 46% sunny, 28 cloudy, 26 rainy. But why does it always settle, and how fast? Every matrix has a hidden set of numbers that act like its fingerprints, its eigenvalues. Plot each one as a point inside this circle. One of them sits exactly at the edge, at the value 1, and that is the stationary distribution, the part that never fades. Every other fingerprint lives strictly inside the circle, so its influence shrinks a little with every step, which is exactly why the chain forgets where it started. And the closer the runner-up sits to the edge, the slower the chain settles down. Here is a gorgeous way to see it. Any forecast is 3 numbers that add to 1, so it is a single point inside this triangle. The corners are total certainty, and the center is perfectly mixed. Now watch the real magic. Start at the sunny corner, the cloudy corner, the rainy corner, 3 completely different beginnings. Every single path spirals inward and lands on the exact same spot, the green stationary point. No matter where you begin, the chain forgets, and arrives at the same long run. Lift that triangle into 3 dimensions and it becomes even clearer. Each axis is the probability of one kind of weather. Drop in any random 3 numbers and watch. Because the probabilities must add to 1, every valid forecast snaps onto a single tilted plane, the purple sheet. There is nowhere else for them to live. Now our daily updates are points walking across that plane, and they march straight to the green fixed point. The geometry of the entire long run is just a plane and a destination. And one last view of P itself. Stand each probability up as a tower. The tall peaks are the habits of the weather, the likely jumps, and the short ones are the rare transitions. A Markov chain, in the end, is just this landscape of odds, walked one step at a time. Not every chain wanders forever. Some have trapdoors. Picture a walker on a line who steps left or right at random, but the 2 ends are absorbing. Land on an end and you are stuck there for good. This is the gambler's ruin. Your position is your fortune, and the walls are going broke or hitting the jackpot. The same absorbing random walk models diffusion, stock prices, and how long until a process first hits a boundary. Here is a second example, and it changed the world. Picture 4 web pages linking to one another. Imagine a surfer clicking links at random forever, with a small chance of jumping to a page at random so they never get stuck. That is a Markov chain, and its stationary distribution answers a priceless question. Which page does the surfer spend the most time on? That long-run fraction is the page's importance. Pages A and C, the most linked to, rise to the top. This is PageRank, the idea that built Google, and it is the very same stationary distribution we just watched settle. Once you see Markov chains, you see them everywhere. Google ranks the web with them. Scientists use Markov chain Monte Carlo to sample distributions far too complex to write down, the workhorse behind modern statistics and physics. Every board game with dice, from snakes and ladders to Monopoly, is a Markov chain over its squares. Your keyboard predicts the next word from the current one. Weather models, queuing at a call center, gene sequences, music generation, the list runs on and on. And here is a twist that runs speech recognition and biology. What if you cannot see the states at all, only noisy clues they give off? A hidden Markov model keeps the chain running underneath, out of sight, and you infer the hidden path from what you observe. It is how phones turned sound into words for decades, and how we read the letters of a gene. So what about your phone? Treat each word as a state. After the word some words are likely and many are impossible. That is a transition matrix again, just over a vocabulary instead of the weather. Follow the high probability jumps and the chain writes a sentence on its own. This is a bigram model, a Markov chain over words. An order K chain remembers the last K words, and your phone's autocomplete is exactly this. A large language model keeps Markov's question, what comes next, but instead of peeking at just the last word, it uses attention to weigh every word that came before. It is Markov's chain, all grown up. But that memoryless rule is also a limit. Real language leans on words from far back, not just the last one. The frontier was to keep Markov's question, what comes next, but let the model look at all of the past at once, weighing which parts matter. That mechanism is called attention, and it powers the transformers behind today's large language models. They are, in spirit, Markov's idea, set free from its memory of one. A spite project from 1906 grew into the engine of modern artificial intelligence. In one breath, a Markov chain says the next state depends only on the current one. You step it forward by multiplying with a matrix, and the long run settles to a stationary distribution. That distribution is an eigenvector. It is exactly how PageRank ranks the web, and it is the seed of the models predicting your next word. Here is one last thought to sit with. If your phone, and even a language model, is really just predicting the next state from the current one, then how much of your next word is a free choice, and how much is simply the transition matrix of your own habits? Markov began this whole story arguing about exactly that. If you want the eigenvector that made today's stationary distribution work, go watch the eigenvectors episode. And next in our deep dives, we follow the same what comes next thread somewhere stranger into the imaginary numbers that secretly run reality. Tell me in the comments, free will or just a very deep Markov chain? Next, the same what comes next thread leads somewhere stranger. The imaginary numbers that secretly run reality. Thanks for watching and keep exploring. Next time, Deep Dive 2, Complex Numbers. Please like and subscribe ThirdEye Labs if you enjoyed this video and let me know in the comments.